All right, I guess it's 1:02, so let's get started. Hello, everyone, and welcome to today's seminar hosted by the Princeton AI Club. Our speaker today is Professor Chelsea Finn from Stanford University. She received her PhD in computer science at the University of California, Berkeley, and has been recognized with numerous prestigious research awards, including the Microsoft Research Faculty Fellowship, the ONR Young Investigator Award, the ACM Doctoral Dissertation Award, and the MIT Technology Review 35 under 35. Today, she will be discussing with us her recent work on how to handle distribution shift in the application of machine learning. The stage is all yours, Professor.
Awesome. Thanks for the introduction. So I guess before I start, I definitely welcome questions throughout the talk. I think that it often makes it a better talk if people ask really good questions. So if you have any clarifying questions or just want to learn more about something, feel free to interrupt or maybe put it in the chat or something like that. Great. So as a brief overview of my work, I'm pretty fascinated about this question of how robots can develop broadly intelligent behavior through learning and interaction. And a lot of my research actually involves studying real robotic systems and how machine learning can allow them to develop more interesting behaviors. But today I'd like to talk about a topic that I think is really important to distribution shift and that are really important to machine learning and will eventually be important to robotics, but isn't something that's kind of directly applicable to robotics right now. And the motivation for that is that I think that many of us have seen that machine learning is quite a powerful tool for solving a number of really interesting and challenging problems. In some ways, I think this slide is a little bit out of date with all of the recent advances with like DALL-E 2, Imagen, Flamingo, whatever your favorite model is. That said, even though we've seen arguably really impressive advances in machine learning, we know that machine learning works really well on the distribution of data that's represented by the training data. And in practice, there's actually this assumption of the training distribution and the test distribution matching is broken all the time in practice. And so what I'd like to talk about today is scenarios in which this assumption is broken and some techniques that we could possibly use to address that. Now, to dig a little bit more into this, I'd like to start by just giving several examples of where the distribution has shifted over time. The first example is from robotics. I think robots are pretty cool. And in particular, if you want to train a robot to learn how to do something like closing a drawer, and you have a data set of behavior, the robot doing like a data set of a robot interacting with the environment from some previous work, and you want to train a robot from that static data set in order to learn a policy, it turns out that there's going to be this distribution shift between the policy represented in the data set and a policy that's being optimized. And if you don't actually account for this distribution shift, you get a policy that when you try to train it for closing the drawer, it exhibits a behavior that doesn't succeed. It has a 0% success rate. It is actually also quite unsafe. So this is one example. Another example is distribution shift over time. So for example, back in 2009, some researchers at Google were trying to predict flu incidents from search queries. And they had a pretty cool paper that showed that you can get a 0.97 mean correlation with CDC data of the flu incidents, which is pretty impressive. But then in February of 2013, the same model that was showing really good performance over time was predicting double the incidence of the flu and wasn't very accurate. And likewise, if you look at modern language models, if you evaluate them over time into the future, their performance gets worse and worse at modeling the language over time because of this temporal distribution shift. So those are a couple examples. A couple more examples that I'll mention is domain shift and subpopulation shift. So say that you're trying to predict the toxicity of comments on the internet so that you can help moderate content on the internet. It turns out that you can create a classifier that gets 92% test accuracy on predicting whether or not a comment is toxic or not toxic, which seems quite great. But then if you look at the performance of this model on comments that mention different demographics, the performance dropped significantly from 92% to as low as 69% on non-toxic comments mentioning the Black demographic. And so this is problematic not just from the standpoint of distribution shift if the population of users changes over time, but it's also problematic from a fairness standpoint. And then one last example from a completely different domain is if you want to predict the biological activity of different molecules, you can get a reasonable precision on new molecules from scaffolds represented in the training data set. But then when you evaluate on new scaffolds, molecules from new scaffolds, your performance drops significantly. So this is just a kind of a diverse array of examples where distribution shift comes up fairly frequently. And if you're interested in actually studying these kinds of problems, I'd encourage you to take a look at the WILDS data set, the WILDS benchmark. These two data sets are examples of 10 of the data sets in the benchmark that have distribution shift, ranging from problems in ecological conservation to medical imaging. And we really tried to create the data set with naturalism in mind. And we talked to domain experts about the kind of distribution shifts that come up in practice. And if you have any feedback or thoughts on the data set, I really encourage you to reach out to Pengwei or Shiori. They did a really fantastic job putting together the benchmark, and they're always kind of looking for feedback or input on the benchmark. Great. So hopefully I've convinced you that distribution shift is a problem in practice with machine learning systems. Now, I think it's useful to think about what is actually going on under the hood here. So I think there's a few different kinds of distribution shift that we might care about. At a very coarse level, we can think about it in terms of 3 different categorizations, in terms of covariate shift, which is changes in the distribution P of X, the distribution over the inputs. We could have label shift, which is changes in the marginal label distribution, or we could have concept shift, which is actually changes to the underlying function itself. And of course, this is just a coarse categorization to be used. Great if we had even more fine-grained categorization, but this I think is still pretty useful for thinking about the kinds of distribution shifts that we want models to be robust to. Now, before I dive into some of the work that we've been doing, I'd like to mention a couple of existing approaches for tackling distribution shift in machine learning. The first class of approaches is approaches that try to essentially rebalance the data in order to prepare for some shift in the density of the data at test time. And in a nutshell, what these approaches do is they try to upweight or upsample data points that are underrepresented. And these could be data points in which your model has high error on. It could also be data points where maybe is low density under the training distribution. And there's a number of classes of approaches that I think, or a number of approaches that fall under this kind of broad class of trying to rebalance the data. They're actually fairly effective at being robust to certain kinds of distribution shift, including domain shift and subpopulation shift. A second class of approaches that I think is also quite interesting is methods that try to learn invariant representations. And in particular, what these approaches try to do is they assume that you have your data is broken into different domains, and you try to learn a representation that is invariant to the underlying domain, such that when you see data from a new domain at test time, you're able to make accurate predictions on that domain because your model is invariant to the domain. And there's a variety of approaches that fall under this category, such as domain adversarial neural networks and invariant risk minimization, as well as a recent approach that we looked at with selective augmentation. And at a high level, both of these kinds of approaches, data rebalancing and domain invariance, can produce models that are robust to spurious correlations and to domain shift. And I'd encourage you to take a look at them if you're interested in these kinds of distribution shifts. But they have a couple downsides as well. So they may require domain annotations. You may need to know for all of your training data points, which domain did that data point come from? And sometimes it's difficult to get annotations from these domains. And second, first, these methods don't address concept shift. If the underlying function is changing, these methods won't be able to help you. And they also won't be able to handle more extreme forms of subpopulation shift, such as very extreme spurious correlations. And so in this talk, I'd like to talk about some approaches that can start to address some of these challenges and start to develop approaches that can handle extreme subpopulation shift and concept shift. Now, I should also mention that all of the methods for distribution shift, including these methods, as well as the methods that I'll present today, they need to go beyond the standard IID assumptions of our training data set. And so, and this is kind of just a fundamental fact. If we want to be able to generalize more effectively with distribution shift, we need to introduce new assumptions. And a key design choice will be trying to design methods that require fairly lenient assumptions, assumptions that hold in practice, that aren't difficult to meet in practice. Okay, so in particular, today I'll talk about two different approaches, and both of them are going to be scenarios where we're going to try to address concept shift and address extreme spurious correlations by actually considering some sort of adaptation as part of the procedure. And in particular, we're going to be looking at extreme covariate shift by training a diverse ensemble and then adapting which model in the ensemble that we're using. And we're going to look at addressing concept shift by trying to edit models at test time post hoc. In the first class, in the first set of methods, we're going to be looking at supervised learning and reinforcement learning settings. And in the second part of the talk, we're going to focus on editing large language models, although a lot of the underlying ideas will be applicable to other kinds of machine learning models. Great. So now let's first start by looking at kind of an extreme form of subpopulation shift. And we can look at an example, a really simple example. We'll look at more complex like image classification problems in the experiments, but we'll start with a really simple example where we want to be able to classify between these two different classes. There's two underlying features. So it's just a two-dimensional classification problem where we have some positive training examples in blue and some negative training examples in red. And what I'm showing in gray here is the gray points here are going to correspond to the test examples with some unknown label. Now, one thing you might note here is that this problem is kind of fundamentally underspecified. There are a lot of functions that can achieve low training loss here, and they can't all be correct. They all agree with the training data set, but they all make actually, these different functions may actually be making different predictions on the test examples. And so we need to be able to figure out which feature the model should use. And we're going to need some additional information to figure this out. And we're also going to need a model that, or an algorithm that can cope with the ambiguity of this problem. And so inherently, what we're going to try to do is, instead of trying to learn a single function, a single classifier, and just output that single classifier, we're actually going to try to learn a set of functions. And we're going to try to learn multiple functions. This could be just a set of completely separate neural networks. It could also be a neural network with multiple different heads. A neural network with multiple different heads is going to be less expensive than a full ensemble, although either could work. Now, if we want to train multiple functions, of course, we could just consider training a standard ensemble of neural networks. But unfortunately, if you train an ensemble of neural networks on the example that I showed on the previous slide, it turns out that it won't actually learn very diverse functions. It will learn a set of decision boundaries that are actually very similar to one another. So we want a more diverse set of functions. And so there's this question of how might we try to diversify the set of functions that we're training. And so one thing you could consider doing is, if we go back to this example, you could try to learn a set of diverse functions that make different predictions on the training examples. But unfortunately, if you did something like that, the training examples are exactly the parts of the distribution that we have a lot of confidence on. And so we know what the labels are on the training distribution, and so it doesn't really make sense to diversify on the training examples. And so instead, what we're going to do is, we actually want to be making diverse predictions on the test examples, on the examples that we are less certain about. And so what we're going to do is, we're actually going to train a diverse set of models that tries to make differing predictions on test examples. And then you might say, well, okay, does this mean that we need test data to do this? Are we cheating? And one thing that's kind of cool here is you can actually train a model to make diverse predictions on test examples without actually knowing the labels of those test examples. And so specifically what we're going to do is, we're going to train a set of functions that minimize training error and which maximize disagreement on unlabeled test data points. And so what this will give us is this will give us a diverse set of functions that all agree with the training data while making differing predictions on parts of the distribution that we're less certain about. And so in particular, we're going to train a neural network with multiple heads. And we're going to try to encourage these to be diverse from one another. And in particular, they're both going to be data points that agree with the training distribution, that agree with the training data, but that make differing predictions on test examples. And so, for example, if we took the 2D classification example that I mentioned before, what we might get is two decision boundaries, one in red and one shown in blue, where both of these are accurately kind of separating the positive and negative labeled examples, but they're making more differing predictions on the unlabeled data. More specifically, in terms of this diversification loss, what we're going to do is we're going to minimize the statistical dependence between the predictions of two different heads. And in particular, we're going to minimize the mutual information between these two different heads, which corresponds to the KL divergence between the joint and the product of the marginals. And it turns out that this quantity you can actually compute in closed form for categorical distributions. And so because we're going to be focusing on classification examples, we can compute this in closed form.
Could I ask a clarification question? I'm not familiar with neural nets with multiple heads. So is that just a shared architecture? Like, yeah, could you just clarify what exactly that means?
Yeah,
Thanks.
so what I mean by there is that we're essentially going to have a neural network with a shared backbone. So they're going to have the same exact, the first several layers of the model are going to be the same exact layers with the same parameters. And then after those few layers, we're going to have essentially separate neural networks that take as input the features of that initial part of the model and produce different predictions.
And then the shared part is like in terms of like training this this network. How does that? I mean, yeah, is the shared architecture trained on this loss, and then yeah, how do you train the network with multiple heads?
Yeah, so all of the parameters of the model are going to be optimized with respect to first minimizing training error of all of the predictions. So we want all of the heads to be accurate on the training data points. And then we're also going to train all of the parameters so that they minimize this term right here. And so this will be training the heads as well as the shared backbone as well. In practice, it's possible that you may only need to train the heads on this last term, but it's straightforward to backpropagate the loss all the way through the model.
Okay, awesome, thanks.
Great. So this is what we're going to do to try to learn a diverse set of functions, such as these decision boundaries right here. Now, the next question is, how do we actually figure out which of these functions is the function that we ultimately want to use at test time? And this is where we're going to need some additional assumptions. So we already introduced one assumption, which is that we're in this transductive machine learning setting where we have access to unlabeled test distribution data during training. And we're going to introduce one more assumption in order to try to disambiguate the correct function. And it's important to introduce this because the problem is, as I mentioned before, fundamentally underspecified. And so we need a little bit more supervision to help figure out what the correct function is. So there's a few different ways that we could do this sort of disambiguation to try to pick which head or which function we want to use. This conceptually simplest thing that we could do, although not necessarily the best choice in practice, is to just randomly label some of your test data points, a few of them, and then select the function that has the highest accuracy on those labeled test data points. This is pretty simple conceptually, although we could actually do something better than this, which is that we can actually actively pick a few test data points that are the most disagreed on and actively ask for the labels for a few of those test data points and then use that to select the head. And so what this would look like is, in these examples, we could look at the data points that the models agree the most on. So maybe, for example, it's this data point right here, and then ask for the label for that data point, and then use the model that gets that question right, or gets that label right, and kind of return that as the final model. So this is going to assume that we can ask for a few labels on the test data set. You could also potentially get away from asking for any test labels whatsoever by just trying to inspect the learn function. So for example, you could try to understand which features each function is using interpretability methods, like GradCam or something like that. And if you can actually interpret the features that that the functions are using, then you can actually use that to pick which head to use, rather than actually any sort of test labels. And so if we have good enough interpretability methods, this latter approach can actually allow us to disambiguate without any additional labels. Cool. So at a high level, the way the method works is first we learn this diverse set of functions by training a set of models that all do well in the training distribution and make differing predictions on unlabeled test data. And then we disambiguate by trying to figure out which of those functions is the kind of correct underlying function, either using a few test labels or by inspecting the features. Great. So now let's look at some of the results. So the first thing that we did is we tried this on the 2D classification problem that I mentioned before. And here's a visualization of the training process of the first stage of this div-dis or diversify and disambiguate method. And what we see is that if we just train two heads, we actually get very different decision boundaries on this problem that are able to kind of learn. One of them essentially uses feature 1 and one of them uses feature 2. And you can also not just train 2 functions, you can also train 10 functions. And if you do something like that, in this case, if you train 10 different linear functions, you'll get actually not just the models that use each of the 2 features, but you'll actually get a spectrum of models that cover the space of functions that are consistent with the training data. Cool. So now let's move on to things that aren't just 2D classification. And in particular, we're going to look at image classification and language classification problems. And for this set of experiments, we're going to try to design data sets that have perfect correlations between some spurious attribute and the corresponding label. And so, for example, in the water birds data set, we're trying to predict whether or not the foreground bird is a land bird or a water bird. And the spurious attribute is the background. And the background is either on water or on land. And we're going to construct a form of this water birds data set that has a perfect correlation between the bird and the background in the training data set. And in our test examples in our test data set, that correlation is going to be broken. And so we're going to have perfect correlation in all of our training data points, and then our test data points are going to either have an imperfect correlation or no correlation whatsoever. And then we're going to measure both average accuracy as well as worst group accuracy, which is essentially if you were to pick the subpopulation of the data that the model does worst on, what is its accuracy on that? Great. And then we're going to compare to a few different prior methods. We're just going to compare to standard neural network training, like empirical risk minimization. We're also going to compare to 2 prior robustness methods. One is called JTT, which tries to upweight the examples with the highest error, and group DERA, which upweights the group of data points that has the highest error. Now, I should mention that none of these methods are really designed to handle ambiguous machine learning problems. They're not designed to handle like this sort of perfect correlation setting. And so, and in general, I guess we don't know of actually any prior methods that are really designed to handle this. And so these are going to be more of a kind of a naive point of comparison that illustrates kind of the difficulty of the problem. Great. So we looked at 4 different data sets, including the water birds data set that I mentioned, as well as 2 variants of SLEBE, where there are different spurious attributes, and this multi-NLI and language classification data set. And what we see is that these existing methods struggle, as we would expect. And sometimes they actually even do worse than random guessing on the worst group. And this is because they're likely paying attention to the spurious attribute that is maybe simpler than the core attribute that the model should be paying attention to. And then if we look at the div-dis method that I mentioned before, and here we're going to be using 16 labels, 16 test labels that were actively queried by the model. What we see a 25% improvement in worst group accuracy on 3 out of the 4 data sets. And on the 4th most challenging data set, we still see like around a 10% improvement. Cool. So kind of overall, we didn't really expect these prior methods to do well, but what this shows is that DivDis is able to handle this really challenging scenario where their training data set is completely correlated, and you just need, in this case, 16 labels to help figure out what the correct function is. We looked at a couple other settings as well, not just this like extremely challenging setting, but we also looked at the original Waterbirds and Slebe benchmarks, which don't have a perfect correlation in the training data set. They still have a strong correlation, but not a perfect correlation. And these benchmarks are settings where prior methods actually showed pretty good results on the benchmarks. But one thing that often isn't kind of brought to the forefront is that these prior methods tune the hyperparameters of the method with respect to worst group accuracy. And this means that you need access to the spurious, like the labels of the spurious attribute during hyperparameter tuning. And importantly, this is kind of an important observation because this means that you have to be aware of the spurious correlation in your training data set during training in order to get a model that is robust to that spurious correlation. And so the way in which you can see this in this table is that if you look at the performance tuned with respect to average accuracy on the training distribution, these numbers are much worse than if you were to tune the hyperparameters with respect to the worst group accuracy, which is what these prior methods typically report. And in contrast, the DivDis method, it actually is you don't need to tune the hyperparameters with respect to group labels. We find that actually if you tune it with respect to the average performance on the training distribution, you actually get you don't see this drop between worst group and average. And when you're tuning on the training distribution, you actually get much better performance than these prior methods. And so this is important because it means that you don't actually need to know what the underlying spurious correlation is when you are tuning the method. You can also see this from this visualization where there are basically just two key hyperparameters of DivDis. One is this diversify term. The second is our additional regularizer that we add. And these plots are showing the performance of it's showing the performance of for these different hyperparameters for average accuracy on the training distribution, average accuracy on the target distribution, and worst group accuracy on the target distribution. And because these plots all look pretty similar to one another in terms of their colors, this means that if we tune on one of these distributions, we'll also get pretty good performance on the other metric. Great. And then a couple other miscellaneous experiments. We also looked at other ways to ensemble, and we looked at this on the Waterbirds completely correlated setting. And what we find is that if you kind of use standard ensembles, or if you use this prior method for trying to learn diverse ensembles, essentially, like I mentioned before, ensembles don't learn a diverse set of functions. And it is also really important to disambiguate. If you learn standard ensemble and ensemble it, then you get slightly better performance if you disambiguate, but a lot of the performance gains actually come from diversifying on the test distribution. And then lastly, we also looked at a domain adaptation problem in the WILDS benchmark, this chameleon problem. And we wanted to compare to this because there are actually a number of domain adaptation methods that also make this assumption of accessing unlabeled test data. And here we find that DivDis doesn't just work for subpopulation shift, it also works well for domain shift problems. And it compares favorably to these prior domain adaptation methods. Great. So to summarize, this approach of diversifying and then disambiguating tackles underspecification in machine learning problems. We found that existing methods really struggle on data that have severe underspecification via complete correlations. To deal with underspecification, DivDis tries to learn multiple different hypotheses underlying the training examples, and then it performs well by essentially learning those multiple hypotheses and then disambiguating with a few examples. And we found that this performs well on completely correlated data, and also on other data sets that can be tuned just using class labels without any group information. Any questions on this before I move on?
I had a question. I was curious how interpretable the predictions are from each of these heads. Like maybe one of the heads is sort of outputting the right classification, land versus water. But maybe one is outputting something like, I don't know, red versus green bird, or a certain type of feather versus another type of feather.
Yeah, that's a good question. So in general, on the waterbirds data set, it would be like in the test data set, we are basically giving it, like a balanced set of like, basically the foreground bird and the background are no longer correlated in the test data set. And so to do well on this, you do actually really have to be paying attention to the foreground. So we know just based on performance that they're paying attention to the foreground. Although it's a little bit difficult to say that like what particular features they're using to classify whether it's a water bird or a land bird. We also did try using interpretability methods on a different data set, actually, that's not one of these. We took the CFAR MNIST data set, which basically just concatenates CFAR images and MNIST digits. You can correlate the MNIST digit and the CFAR digit, and unsurprisingly, the models like to pay attention to MNIST rather than CFAR because MNIST is a lot simpler. And on that, we tried using interpretability methods to tell whether or not it was paying attention to the MNIST digit or the CFAR image. And there we were able to very clearly see which image it was paying attention to by using GradCam. That said, I think that in terms of more fine-grained features, I think that the field of interpretability has still a while to go to figure out exactly what features models are using. And that's, I think, a pretty interesting research direction that is fairly open.
So I guess just like by the eyeball test, it's not super obvious, I guess, what features it's using. Does it look kind of random, essentially?
Yeah, I think that at least in my experience, interpretability methods are not quite as good as I would like, although it's also not a research area that I work on very much myself. So experts in interpretability have probably a more nuanced answer there.
Cool.
Cool. So as an additional aside, so I talked about diversifying in supervised learning settings, and we can actually also learn diverse ensembles of reinforcement learning policies. And in particular, we were again looking at a robustness setting where we have a training environment such as this walker trying to kind of walk forward on a plane. And we considered a number of different test environments, such as when there's an obstacle in the way, such as when there's a force applied to the walker, or such as when some of the joints are disabled. And what we can try to do is we can try to learn a diverse ensemble of RL policies such that one of those policies still works well in the test environment. And so we can essentially take the same ideas we talked about before, where we're going to try to learn multiple solutions to the training MDP and then pick the solution that works well in the test scenario. And so in particular, if we look again at a really simple example where we're trying just to get from A to B on this in this world, if we learn multiple different ways to get from A to B, this means that at least for some test environments, when there's a local change in the environment, such as an obstacle right here, it turns out that if you learn diverse ways of getting from A to B, then one of those solutions is more likely to work in these out of distribution test environments than if we were to just learn one solution. And so what we can do is we can, if we assume that we can adapt with a modest amount of data and make some assumptions about the changes to the environment, namely that the changes to the environment are local, then if we can learn these diverse solutions to the training MDP, then we can actually be robust and we can actually extrapolate to environments that are that weren't seen during training. There's also a way to formalize what I mean by kind of these local changes. Essentially, we want the optimal policy in the test MDP to also do well in the training MDP. Essentially, we'll use that in our formulation of the method. Now, there's this question of how do we actually learn these multiple different solutions? And what we're going to try to do is learn a controllable space of diverse policies. And it's really important that we don't just learn like diverse trajectories that get to the goal. We want that to actually be able to control which solution we're using to get to the goal. And to do this, we're going to try to basically introduce a latent variable into the policy that controls which solution you're using to get from A to B. And then we can formulate a constrained optimization such that all of those solutions are good. So all of those solutions achieve a return within epsilon of optimal. And so in particular, we can set up an optimization problem that looks like this, where this may look a little bit complicated, but essentially we're going to just maximize the mutual information between the states visited and the latent variable being passed as input to the policy. And we can decompose this into these two entropy terms. And then we essentially want the second term is just saying that we want all of the solutions of our policy, the return of all those solutions to be within epsilon of the optimal return. And then at test time, once we have this latent variable policy that can solve the task in all of these different near optimal ways, then what we just need to do is we can basically need to pick the different z, and so we can roll out k policies, but each with a different z, and then return the basically return the policy with the best performing latent variable. Cool. And so we evaluated this method in comparison to just standard reinforcement learning with soft actor critic, in comparison to a method that only diversifies and doesn't consider the reward, as well as a prior robust adversarial reinforcement learning method. And we measured 5-shot generalization to these extrapolated environments, where we're going to be plotting how much the environment is changing over time versus performance. And so as the environment changes more and more from the training environment, we expect performance to start to decrease because we're forcing the model to extrapolate more and more. And overall, what we see is kind of this approach, again, of learning these diverse policies and then adapting the solutions at test time generally performs pretty reliably, at least in 4 or 5 out of the 6 environments that we considered, and is significantly better than prior robustness approaches and prior methods that only diversify or only optimize reward rather than optimizing both. Great. So I guess the takeaway of this first part is that if you learn a diverse set of classifiers and policies, this actually allows us to very quickly adapt to extrapolated situations. Cool. So these were approaches for addressing kind of forms of covariate shift, basically forms of changes to the kind of the support of the data that the model is seeing. However, these approaches aren't going to help you when the function itself is changing, when the function that you need to, the kind of the underlying, the true model of the world is changing. And so this is what I'd like to talk about in kind of this second part. Like I mentioned before, we're going to focus on large language models here. And let's maybe start by looking at a few examples. So we can take a pre-trained model. We can take GPT-3, for example, and say we ask it, what is the largest English-speaking EU nation? And it turns out that it will tell us the United Kingdom. And of course, the United Kingdom is no longer part of the EU. And so this answer is out of date, and the answer should be Ireland. We can also ask it, who is Algeria's current president? And it will also give us an out-of-date answer. And likewise, if we ask it the club team that Leo Messi plays for, it will also give us a club team that Leo Messi used to play for, but not the current club team of Leo Messi. And so these are examples of concept shift because the correct answer is actually changing between training and test time. And what we'd really like to be able to do here is we'd like to be able to keep large models up to date, despite the fact that we have concept drift over time. Of course, one solution to this problem would just be to continually retrain the model, but fine-tuning these really large language models like GPT-3 is super expensive, and it'd be nice if we had a way to kind of more quickly kind of patch or edit the model when we see something changing. So we'd like to be able to essentially make these edits to machine learning models kind of analogous to how we can patch software. And in particular, what I mean by this is, say we ask the model who is the Prime Minister of the UK, it gives us an out-of-date answer. We'd like to be able to say, okay, now for this input, I want the model to be edited so that it actually gives me the correct answer. So we're going to give it this XE and this YE that corresponds to an edit that we want to make to the model. And we want to be able to pass this edit into a model editor that can tell us, that can basically produce a version of the model that's now edited, and that gives the correct answer when we ask that question again. And also if we ask a rephrasing of the question, or if we ask something that is if we ask, for example, who is the UK PM, or if we ask it, is Boris Johnson the UK PM, it will give us an answer that is consistent with the edit that we made to the model. And so we want to be able to edit models like this. And when we make those edits, we also don't want the model to change on unrelated inputs. And so if we ask it an unrelated input, such as who does Messi play for, we don't want the model to be affected by the edit that we made to something unrelated. Okay, so this is like, I guess, the dream that we have for being able to edit these large neural network models. And one way that we can formulate this problem is as kind of essentially a sort of a meta learning problem. And in particular, this formulation was introduced by this work by Sinitsin et al. At ICLR 2020, and we also kind of expanded the formulation in a paper at ICLR this year. And in particular, what we're going to the way that we're going to think about this problem is we're going to assume that we have some data set that kind of an editing data set, a data set that kind of can allow us to train a model editor, that can allow us to teach a very small model to learn how to edit a very large model. And as an example of this edit data set, we will have an edit descriptor that kind of describes the edit that we want to make. This could be, for example, an input-output pair. It could also be something a little bit more abstract. And then we also want, for this given edit descriptor, an example of something out of scope from that edit that shouldn't be changed, as well as something in scope from that edit that that should be changed based off of the edit that we're making. And so in particular, we're going to try to enforce locality of edits by giving an example of an out of scope example, such as what team does Messi play for. And then additionally, we're going to try to enforce generalization of the edit with these in scope examples. And then once we have a data set like this, then we can actually train an editor to be able to make edits like these examples in this edit data set, such that then later when we want to actually go and edit our model, we can use a model editor to very, very quickly make edits to our model. Okay, and so now there's been a couple of approaches that were actually introduced in these two papers for editing neural network models. And they work reasonably well, but we found that they struggle in a few different important circumstances, like when you want to apply a large number of edits. And so next I'm going to present an approach for editing that we found to be quite robust and quite effective for editing large language models. And so we refer to this as semi-parametric editing with a retrieval augmented counterfactual model, which is a bit of a mouthful. But in essence, we're going to start with our base model, so our kind of pre-trained large language model. Then we're going to store edits in an explicit memory of all of the edits that we want to apply to that model. We're going to have a scope classifier that classifies whether or not an edit is within scope for a given test input. And lastly, we're going to have a counterfactual model that essentially can predict whether or not, that can make a corresponding prediction for an input and the corresponding in-scope edit. And so I guess what I mean by this is we'll fill up our edit memory, and we will, for a new test input, we'll ask the scope classifier, are any of these edits relevant to this input? Then we will find that one of them is relevant or not, or none of them are relevant. If one of them is relevant, then we'll pass both the input and the edit to our counterfactual model and ask our counterfactual model what is the correct answer, given that we want to apply this edit to the model. And likewise, if we get an input that isn't related to any of our edits, it's out of scope, then we will just directly pass, our scope classifier will tell us that, and then we'll pass that input to our base model to get the corresponding answer. So essentially, we're just training these two different things, the scope classifier and the counterfactual model, to be able to tell us first whether or not edits are within scope for a given test input, and second, how that edit should actually affect the prediction for the test input. The scope classifier can actually be just trained as a binary with a binary classification setup, And the counterfactual model can be trained, again, with the edit data set to make the correct corrections. Cool. So
Question.
yeah, go for it.
So the counterfactual model does not leverage the frozen model. That seems a little off, right?
Yeah, so in this case, the counterfactual model doesn't leverage the base model. You could, for example, consider passing in the input of the base model. In practice, we actually found that that it works quite well if it doesn't leverage the base model. I could actually imagine some scenarios where maybe leveraging the knowledge of the base model could be pretty effective, especially because it's generally a fairly performant model. But at least for question answering and for sentiment editing, which I'll show experiments for, we actually found that just kind of training this separately, we'll still pre-train this counterfactual model, but training it separately from the base model actually works pretty well.
I see.
So basically, as you get more edits, will your scope classifier and counterfactual model grow in response to the number of edits you make?
So the scope classifier and the counterfactual model, we'll train them once, and then as we apply more and more edits, the only thing that changes is actually just this edit memory. And so these models don't actually need to grow in any way as you get more edits. The only thing that needs to grow is just storing these edits. One question that you could ask is like, what if like Messi joins yet another club? How do you handle something like that? And that's something that this framework doesn't readily handle. But you could imagine, for example, periodically flushing your edit memory by kind of distilling it into the base model. So that if you do that kind of more frequently than Messi changes clubs, then you won't have to handle that problem.
I see. Thank you.
So instead of actually updating the parameters, it seems like it's just a way of retrieving. It's just like a way of directing to a knowledge base or using your GPT-3 model, right? So do you think parameter updates is the right way to frame this? To me, it just seems like you're trying to understand, you have a knowledge base and you're referring to the knowledge base for a few queries. And then.
Yeah, so this is definitely related to kind of retrieval-based language models in some ways. And you can sort of think of it as like, yeah, we're basically, for the things that we want to edit, we're going to basically formulate it as like a retrieval problem and do retrieval for the kinds of, for things that are kind of within scope from the edits, and then otherwise use our base model. So yeah, I think it's definitely like closely related to those approaches. The other two approaches that we'll compare to are our approaches that actually try to directly edit the weights of the base model. And as we'll show in the experiments, those methods, I think they're in some ways they're kind of conceptually cooler, but they struggle to scale to large number of edits and so forth.
Makes sense. Thank you.
Cool. So our first experiments were looking at question answering, which are basically correspond to the examples that I was showing before, like asking like the club that Leo Messi plays for. And we're going to look at two quantitative metrics here. The first is edit success, which is how accurately are we editing our model? Like, what is the accuracy of the QA model on examples that are in scope for the edits that we've applied? And the second metric is drawdown, which is how much is our accuracy dropping on examples that are out of scope from all of the edits that we've applied. Now, we can combine this into a single metric by just measuring edit success minus drawdown. And so the best that you could do on edit success minus drawdown would be 1, where you could have an edit success of 1 and a drawdown of 0. And so 1 minus 0 is 1. And so the best that we can do is kind of is to get a measure of 1. And as this decreases, this means that either our edit success is getting worse or our drawdown is getting worse. And we're going to plot this metric as a function of the number of edits that we're applying at test time. Great. And so here we're going to be editing a T5 large model on question answering problems. And what we see is the approach that kind of the semi-parametric approach that I mentioned on the previous slide. It actually gets performance quite close to 1, even as you increase the number of edits to up to 75 edits here. Whereas these prior approaches that try to directly edit the weights of the base model, they can do reasonably well when you're only applying a single edit, but as you increase the number of edits, they really start to struggle much more, to the point where they're not very successful at editing, and they're also adversely affecting inputs unrelated to the edits. And so kind of at a high level, only the semi-parametric approach is able to achieve high edit success with low drawdown on this question answering setting. Now I'll just show one additional experiment, which was actually not editing factual knowledge, but actually trying to edit the sentiment of models. And here we're going to be editing Facebook's public Blender bot model. And it turns out that if you actually ask Facebook's model, what do you think about vaccines? The original model is actually quite negative about vaccines. And so what we're doing here is these are actually outputs from the model, and we're labeling them as either positive, negative, or autism related. And we see a lot of red and pink here. And what we can do is we can train a model to be able to edit sentiment for a variety of different topics, and then try to edit this model specifically for the sentiment around vaccines being more positive. And after we edit the model, we get predictions that look like this, where overall you see much more yellow, so it's much more positive. And qualitatively, it's not just more positive in a superficial way. It's like actually saying, it's not just saying things are great, but it's saying that, for example, I think they are a good way to prevent infectious diseases. I think it's important for people to be informed about the risks of their health. And so, yeah, this is editing is not just these kinds of models aren't just good for editing factual knowledge. They can also be used for editing the sentiment of models for different topics. Great. So I guess the takeaway for the second part of the talk is that we can train these post hoc editors for very large language models. And this may help practitioners address concept shift over time. Well, they could also help address covariate shift, but they can also address concept shift, which is I think a particularly challenging form of distribution shift. And kind of overall, I think that both of these kinds of approaches are kind of examples of models where you aren't just training a single model that's going to stay fixed forever. We're either going to train a collection of models and then try to adapt which model we're choosing at test time, or we're going to train a model that, or train something that allows the model to be flexibly edited, depending on how things change over time. Great. So with that, I'd like to thank my students, and in particular, the kind of work that I presented was led by Yoonho Lee right here and Eric Mitchell. Also, if you're working on distribution shift, I definitely encourage you to take a look at the Wilds benchmark. And yeah, happy to take more questions as well. Thanks.
Thank you so much for that presentation. Like this work is super cool. One question I had was just about this last project. And so in particular, it seems that you have to already have formed this edit data set. And so one question I had was whether you can think of whether you've thought at all about kind of automatic ways to kind of almost do change point detection to detect the changes in the environment and then kind of almost automatically create the edit data set.
Yeah, absolutely. I think that something like that would be really interesting. And you could do this, you could do some sort of change point detection to construct an edit data set. You could also, even if you you could also kind of pre-construct an edit data set to train a model editor, but then not necessarily require a human practitioner to tell the model what edits to make, but say, I read in the news that Biden is now the president of the US. Let me edit the model so that when someone asks me who the president of the US is, I will give it the correct answer. And so I think that something like that could be really interesting to look at. It's definitely not something that this work solves at all, but I think that, yeah, it's not something that's trivial to do, but I think that something like that could be really cool to allow models to basically automatically stay up to date by reading the news or looking at other information.
Thanks.
Okay, so I guess I also have a question. So it seems like, so my general impression is that it seems like basically the approach to handling the potential for distribution shift is essentially to have, in some sense, a larger model or models, for the case where you have a diverse ensemble, that's obviously just I guess a bigger construction to just have a single model, and in the where you're doing this, basically having a model editor, it's in the sense you're having this auxiliary like helper model on top of your original model. So do you think this is kind of just like something that's basically unavoidable because of just the nature of the task, or maybe is there some kind of a way to formulate it in the sense that, and did you have any like particular idea why the other examples where you shown, like the large language model, where they're actually trying to change the parameters of the old model, kind of performed worse than this case where you had an auxiliary model? And do you think there's a way to get around this?
Yeah, I think it's an interesting question. I think that in some ways I view these maybe as tools for allowing us to kind of adjust or change tools for allowing us to kind of go beyond kind of training single neural networks to minimize training error. I will say that I guess in the second example, we are kind of creating this wrapper around a model that does make the original model bigger in some ways, although each of the components can actually be trained completely separately. In this first case, actually, by training this ensemble can actually be really not that much larger than the original model. You can even just have these heads be just different final layers of the model. And we've also found that, this isn't in the paper, but we've kind of ran some experiments where you can just kind of pre-train an entire model and only kind of fine-tune different heads on top of it. And so I don't think that this necessarily needs to be substantially larger than the original models that we're training. And it may even be that you can actually train a smaller models that still have a couple different heads. So I don't think it necessarily needs to be that much bigger per se. I think of it, I guess, maybe more as tools for going beyond training single functions that never change.
Yeah, I guess it'll be interesting to consider exactly how much adaptability and the variability you can get for a neural network model by just changing its final layer.
Yeah, and there actually are a couple papers that have looked at that recently. I can't remember, unfortunately, the authors of the papers, but there's one paper that shows that you can actually, if you just retrain the final layer, you can actually you can get a model that adapts to domain shift very effectively. And I think that there's another paper that did the same thing for subpopulation shift. And so it does actually suggest that, at least for computer vision problems, which I think that they were focusing on, the models are actually learning pretty good features, not just of the spurious feature or of the domain, but also the core feature. And you just potentially just need to train that last layer. So yeah, there's evidence of that. I'd be happy to send you kind of pointers offline if you're interested.
Yeah, I think that's very cool. Yep. All right, so I guess if there are no further questions, let's give another fictive round of applause to Professor Finn for her very interesting presentation.
Thanks for hosting.
All right, and I guess just also to briefly mention, we will be having more of these seminars throughout the summer, so be sure to look out for further notifications from the Princeton AI Club. All right, thanks everybody for coming out today.
Okay. Thank you.
Thank you.
Bye. Bye.
Hi, sorry. Can I ask a quick question? I know it's a bit, if you have to go, let me know, but
yeah, happy to.
So I read a book about covariate shift, and it was like quite different. It was about like a regression method where you had to estimate the weight to take into account the shift in the covariate. So you would like have these weights that would then change from one distribution to the other, and then the weight would actually be the ratio between the two distributions, right? Evaluated at that training point. How would you say is like the difference between this approach to covariate shift and the one you're doing?
Yeah, so I think that you're kind of referring to like importance sampling based approaches. And I think that it's those approaches are like very much like like kind of form some of the foundations, I feel like, of some of the work in distribution shift. One, I think that there are a few different differences, but maybe one that I'll highlight is that in the examples that I showed, we're actually looking at scenarios where your test distribution, some parts of the test distribution have zero support in the training distribution. And so if you just try to reweight, approaches that reweight or approaches that upweight, they fundamentally aren't going to work because you don't have any of the training data points in those regions to actually upweight. And so
I reached that exact problem. So,
yeah, exactly.
And so in the method you're proposing, we can actually like not need the test support to be contained in the train support kind of.
Yeah.
Okay. Do you have the papers out on archive already, or?
Yeah, so the first paper is out on archive. And so yeah, that should be fairly straightforward to find. The second paper is not quite on archive, but I could send you a link to, we have a public link and it's almost on archive.
Yeah, thanks. Yeah, I appreciate it, because I studied this and I bumped into the problem you described, and I was like, well, this serves me nothing, right?
Yeah.
So yeah, thanks a lot.
Yeah.
Yeah, can I put my email on the chat so you can send it?
So I just put the first paper is in the chat. I think that's probably the one that you're more interested in, but I can also send the other link as well. Yeah, here's a link to the second project.
Thank you so much.
Yeah.
And great talk, super clear. Thank you. Bye, have a great day.